Hi, I hope everybody's doing well today. We are going to start the Module 2 notes for domain and range. You will probably get this video in a couple parts. I'm visiting with my aunt and uncle this weekend, so I'm recording here and there when I can squeeze it in. Alright, so here's my quote for the day. If people do not believe that mathematics is simple, it is only because they do not realize how complicated life is. So as I mentioned, we're going to be focusing on domain and range in this set of notes. And we actually touched base on this a little bit in the last set as well, but we're going to go into more detail. Okay. So the first few examples I'm going to give you are domain and range with graphs. Now, keep in mind that when we say domain, we're talking about the x's or that first coordinate, and when we say range, we're talking about the y's or that second coordinate. So when we look at this graphically, since domain is the x's, we're looking from left to right. And when we talk about range, we're looking at the y's, we're looking from bottom to top. So if I take a look at this first graph, I see that the furthest it goes to the left is an x value of -4. So my domain is going to start at -4. The furthest that my graph goes to the right is an x value of 5. Now, we have to talk about parentheses and brackets. If a specific point is included, we use a bracket. If it is not included, we use a parenthesis. So if we check out this point right at -4, we see that it's an open circle. That means that it's not included, and when it's not included, we use a parenthesis. If we check out the point when x was 5, we see that that's a closed circle, so that indicates to us that the point is included, so we're going to use a bracket. Now let's talk about range. When we look for range, we're looking from bottom to top. We're looking at the y values. So the lowest y value that this graph has is at -3, and the highest y value is at 1. Now, when the graph has a y value of -3, it's at that open circle again, so it's not included, we use that parenthesis. When the graph has a y value of 1, that point is included because of that closed circle, so we put a bracket. Now, let's check out our second graph. We've got a little bit of a more funky shape here, but we're going to follow the same idea of domain and range, parenthesis, and bracket. So when we look at domain, remember we're looking furthest to the left and furthest to the right. And we're talking about the x values. So the furthest to the left is an x value of -3. Furthest to the right is an x value of 4. Both of these have shaded circles on both ends, so that means they're included, so we're using brackets. On range, we're looking bottom to top. We're looking at those y values. The lowest y value is at -4. And the highest value is at +3. Now realize that those two, the bottom and the top, don't happen at end points, and that's okay, but we've got to make sure we're going the lowest that graph is and the highest that graph is. Okay? Now, if we look at that y value of -4 where the graph is continuous through there, so it touches that point, which means we're going to use that bracket. Same exact thing at 3. Here's our next two examples. Same thing, we're still looking for domain and range. So on our top graph, if we look furthest to the left, we have an x value of -6. And if we look the furthest to the right, we actually don't have a furthest to the right. Although it's not drawn in there, this graph continues on and on and on forever to the right. So therefore it's going to be a positive infinity. Now, going back to that furthest left value, -6, it's a closed circle, so it's included, we're going to use a bracket. Anytime, every single time you have parentheses or negative infinity or negative infinity, you always use a parenthesis. Now let's check out range. So now we're looking bottom to top. There is no lowest y value on here because that graph keeps going down, 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 down. So my range is going to start at negative infinity. And now if I look for that highest y value, I'm going to see that occurs at a y value of 1. Okay? As I mentioned before, infinity and negative infinity always, always, always get parentheses. That 1 is included in the graph. This comes up, it touches that y value 1, and it comes back down. So that's going to get a bracket. It's included. Now, we've got something a little bit different going on in this bottom right-hand graph. Okay, notice that there's a vertical red line there. That red line there is what's called a vertical asymptote. Now, when we're talking about asymptotes, the graph gets closer and closer and closer to that asymptote, but it never actually touches it. So, when we talk about domain on this graph, and we're talking about left to right, we're going to have a little break in our graph. So, the furthest it's going to go to the left, again, it's not drawn in, but that graph just continues forever and ever and ever to that left side, so it's going to have a domain that starts at negative infinity. Remember that positive infinity and negative infinity always get a parenthesis. Okay. Now, when we look from left to right, we've now got a break in the graph at an x value of 1. So we're going to stop at 1. It never actually touches that value of 1. It just gets closer and closer and closer. So it's not included, which means we use a parenthesis. Then we pick up on the other side of that value of 1, and we go all the way to positive infinity. Now, anytime you have two pieces like that in your domain, you always need to join them with a union symbol. Now let's check out range. Remember, range, we're going bottom to top. Okay? There is no bottom. Both of these pieces of the graph just continue down forever, so that goes to negative infinity. That's going to get a parenthesis. And now if we look up, there's really no top either because it's going up and up and up over here. So we're going to have a range of negative infinity to positive infinity. Now, the domain, when not specified, is all real numbers that produce real numbers. Now, that may seem a little bit repetitive, but we're talking about all the x values that we can plug in that are real numbers that will give us out real numbers as well. Okay? So essentially what we need to do when we're asked to find domain is we need to find values of x that do not produce real numbers. Now, when we find those values of x that do not produce real numbers, we know that those numbers are not included in our domain. Okay? So, let's talk about polynomials first. When we talk about polynomials, automatically, all polynomials are going to have a domain of all real numbers. Okay? So, a few examples. If you came across the polynomial f of x equals 3, okay? There are no values of x that I can plug in that are going to produce non-real numbers. Every single number that's going to come out is going to be 3, and that will always be a real number. Okay. Here's another example. G of x equals negative 2x plus 1. No matter what real number I plug in for x there, I'm always going to get out a real number. So therefore, my domain is all real numbers. How about h of x equals x squared minus x minus 5? Same idea. No matter what real value I plug in for x, I'm going to get out a real value as well. We could also have something like g of x equals x to the 100 minus x squared. Okay? Don't let that x to the 100 throw you off. Any real number I plug in, I'm going to get out a real number. So anytime you come across a polynomial, your domain will always be real numbers. The same is true of absolute value functions. Absolute value functions will always have a domain of all real numbers. Okay? So for example, if I have the function f of x equals the absolute value of x plus 1 minus 3, no matter what value I plug in for x there, I will get, as long as it's real, I will also get out a real answer. Okay? The same is also true with odd root functions. So for example, if I had g of x equals the cube root of x, that would also have real, all reals, it's a domain. No matter what real number I plug in for x, I'm going to get out a real number for my output, for my range. Okay? Now, it's very important that you realize this is an odd root function. When we talk about even root functions next, it's a different scenario, so you've got to pay close attention to if it's an odd root. So when we're talking odd roots, most commonly we'll see the cube root, but it could also be a fifth root, a seventh root, a ninth root, so on and so on. Any odd index will have a domain of all real numbers. Let me go back up to the absolute value. That also will always have a domain of all reals. Okay? So when you come across polynomials, absolute value functions, or odd root functions, those are the easy peasy ones. You know that automatically the domain is going to be all real numbers. Now, the next couple examples I'm going to talk about with you are where we have to start doing a little more work. Okay? Notice that this next function I'm going to talk to you about is an even root function, not an odd root, but an even root. So now we're talking square roots, fourth root, so on and so on. Okay? So if I look at the example, h of x equals the square root of x, my x has to be greater than or equal to 0. As soon as I have an x value that is negative, we're now talking about an output that's imaginary. Okay? Remember, we're trying to find real numbers here. So in our case, when we're asked to find domain of an even root function, we have to make sure that our x is greater than or equal to 0. Okay? So what we always want to do is we want to set the expression that's under the radical greater than or equal to 0 and solve it. So set expression. See if I can squeeze it in there. There we go. Under radical greater than or equal to 0. And once we do that, we're going to solve. You'll see an example coming up with that. Rational functions, we also have to do a little extra work on as well. With a rational function, okay, we're potentially talking about a variable in your denominator. Okay, so an example would be something like f of x equals 1 over x. Okay. Remember that you've probably heard the bottom of your fraction can never be 0, or your denominator cannot equal 0. The same is true when we try to find the domain of rational functions. So, when we come across a rational function and we're asked to find the domain, we need to set the denominator equal to 0. And solve. Okay. When we solve, the values that you get are the ones that you cannot have. Okay, so let's apply what we just discussed about polynomials, absolute value functions, odd root functions, even root functions, and rational functions to some actual concrete examples. Remember that polynomials, absolute value functions, and odd root functions have all reals as their domain. If we have an even root function, we have to set that expression underneath the square root equal to 0. And if we have a rational function, we have to set that denominator equal. Alright, so our first example is f of x equals the square root of 2 minus 3x. So, let me rewrite this so it looks a little bit prettier. Okay, so we're talking about a square root here. A square root is an even index. Even though we don't write it, it's got that imaginary little 2 telling me that this is an even root. It's got an index of 2. Okay? Anytime I have an even root function, I've got to set what's underneath the radical equal, greater than or equal to 0. Okay, so we've got 2 minus 3x underneath that radical. It needs to be greater than or equal to 0. Now, if I solve this, I'm going to move my 2 over by subtracting it. And that's going to give me negative 3x is greater than or equal to negative 2. Now I'm going to divide both sides by negative 3. And remember that when I multiply or divide an inequality by a negative, my inequality sign is going to flip. So I get x is less than or equal to. And remember, a negative over negative is a positive. So I have a 2/3. So my domain is x is less than or equal to 2/3. Now, if I read my directions up here, it asks me to write my answer in set builder notation and interval notation. So we need to take this a step further. If my x is less than or equal to positive 2/3, that means I'm going to start at 2/3. That point is going to be included because it's less than or equal to 2/3. And you know what? I need to rewind. Beep, 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 beep. Okay? If x is less than or equal to 2/3, then I'm actually starting at negative infinity. Okay, so I made a mistake there. So when x is less than or equal to 2/3, the furthest I'm going to go to the left is going to be negative infinity. And the furthest I'm going to go to right is positive 2/3. Okay. Now remember, positive infinity and negative infinity always get a parenthesis. And now because I have x is less than or equal to 2/3, it means that 2/3 included, I get a bracket. Okay. Now, sometimes it can help visually to draw this out as well. Let me show you what that would look like on a number line. If I had a number line here, and I put the number 2/3 on it, let's just say 2/3 is right there, okay? I want everything to the left of 2/3. So I'm talking all this space. And I also want the 2/3 itself because I have that less than or equal to 2/3. So sometimes it can help to see what's going on visually on that number line first, so that you can then write it in interval notation. So just to be clear with you, this is set builder notation, and this is interval notation. Alright, let's look at the next example. Now we have g of x equals x over the quantity x squared minus 9. Okay, I'm going to rewrite this one too to make it look a little bit nicer rather than having it typed out. Oops. It's x over x squared minus 9. Alright, so notice that I have a rational function here. I have a denominator. Okay, my denominator right here, this x squared minus 9, cannot be 0. So what I do is I set that denominator equal to 0 and I solve it. Remember that when I solve it, the solutions I get out are the values that I cannot have. Okay? So I'm going to set x squared minus 9 equal to 0. Now, this is a difference of squares, so I could factor it if I wanted to, but I think the easiest thing to do in this case is going to be use the square root property. So I'm going to move that 9 to the other side, and I'm going to say x squared equals 9. Now I'm going to take the square root of both sides, and remember that when I do that, I get that x equals plus or minus the square root of 9, but the square root of 9 is just 3, so I end up with plus or minus 3. Now again, remember that these solutions I get out are the values I cannot have. I cannot have positive 3 and I cannot have negative 3 because those are the two values that make that denominator 0. Okay? So let's look at what that looks like visually on the number line, because that's going to help us get over to interval notation. So when I look at interval notation, I know that I'm going to have a negative 3 on my number line, and I know I'm going to have a positive 3 on my number line. Okay? Since those are the two values that are not included, those are the two values I cannot have, I'm going to have open circles at those two places. Every other number I can have, so I'm going to shade in the rest of that number line. It's just that positive 3 and negative 3 I can't have. So when I translate this over into interval notation, I'm going from negative infinity to negative 3, union negative 3 to positive 3, union 3 to infinity. Now notice I use parentheses on the negative 3 and the positive 3 because I'm working around those points. Those points aren't actually included. Alright, number 3. This is one that you should be excited to see. Number 3 says h of x equals x cubed minus 5x squared minus x plus 1. Guess what? This one's a polynomial. As soon as we see polynomial, we're like, yes, this one's the easy kind. It's automatically all reals. Now, anytime we have a function that has a domain of all reals, the way that we write that in interval notation is negative infinity to positive infinity. Now remember, those infinities always get parentheses on them. Number 4, that's another one that we're like, woohoo! It's absolute value. Absolute value has all reals. So, in interval notation, we're talking negative infinity to positive infinity. Now, number 5 says g of x equals 1 over x squared plus 1. We've got a rational function here. So this means that x squared plus 1 can't be 0. Okay, now, this one's a little bit of a trick question. Okay, if I set x squared plus 1 equal to 0, will it ever actually equal 0? If I take any number and I square it, I'm going to get a positive number. And then if I add 1 to that, I'm going to end up with an even bigger positive number. So x squared plus 1, a sum of squares, won't ever actually equal 0. So since it's not going to actually equal 0, I can say that this one also has a domain of all reals. So we're talking negative infinity to positive infinity. Now, it was important when we started to realize, oh, this is a rational function. I have to check when that denominator is going to equal 0. And that's what we did. We just found out that in this case, my denominator never actually equals 0. Alright, unfortunately, the last two examples are going to have to wait. My uncle just finished cooking dinner. So I will be back with number 6 and 7 with a part 2 later on.